going on?
All right. So, welcome back. Hopefully you guys had a wonderful Easter, a restful time. Okay. The problem was Thursday. I forgot even about that. We don't want to go there. So, you want good?
I mean, at the end.
Okay. You just need to stay. You throw it all away later. Throw it all away later. Sit.
Now it's awkward.
It's always. Okay. That's fine. Just leave it all right there. It's not going anywhere. Okay. So, on Thursday, before prom, we started talking and working on gas law stoichiometry problems. You're having a test on Thursday over all of this gas laws and gas law stoichiometry. Now, if you look up here, this is basically everything you're going to need to know. Okay, we've talked on all of these, Boyle, Charles, Gay-Lussac's, the combined gas law. We did practice problems in your textbook with these 20 through 21, 21 through 31, I mean. And we went over all of those, and you seem to be pretty good as far as just plugging in the values into P1, V1 over T1 and just solving for those. Then we talked about the ideal gas law, PV equals nRT. Two variations of that are important is PV, and we know that moles is going to be grams over molar mass. So when you have grams over molar mass, you might want to do that separately and get moles and then plug it in for the N and then just do RT. And then the other most important one you probably should just memorize is molar mass is GERD over PIV. Because a lot of times we use this gas law to figure out the molar mass of the gas. Okay, this equation still comes from this. It's just rearranged for the molar mass here, GERD over PIV. But that kind of rings true, and sometimes you can just help remember that. And molar mass is GERD over PIV. And so you can have that. Then we started talking just last week about gas law stoichiometry. And with gas volume to gas volume, they're the simplest ones. You only need the mole ratio in order to be able to solve, and we'll do some more practice with those. Then we were working on these. Whenever we have gas volume and STP, remember that's when we're going to use the 22.4. And then I'm going to, at the very end of today, I'm going to go over this type of problem, but this is going to be a bonus on your test. But as I'm going over this bonus, I'm going to explain this last law, which is a very simple law, simple subtraction for Dalton's law. This is going to be the equivalent of like changing Celsius to Kelvin. Okay, it's a super easy, conversion, and super easy law in order to be able to apply, and I'll tell you exactly when you have to use that. Okay, so this is all the concepts that we're going to have, and you need to be aware of for your test. Okay, now. Tomorrow's just going to be all practice. Tomorrow's going to be review. I'll have practice problems for you. It's called a study guide, and we'll just kind of go through that and just make sure that we're 100% ready for the test on Thursday. Then we're going to come in, we'll do solutions, and then we're going to do acids and bases, and then we're going to be finished. So, on Thursday, if you recall, we were working on that same worksheet that we did just about all these other problems on. So let's get that worksheet out, please. No, well, you need that.
Well, yes.
But that's not the worksheet. Okay, this is what we were working on. Now, we did this one already, but I'm going to go through and do it super fast just for review. So the first thing you have to do is write your balanced equation. Okay? There it is, right there. That's it. You're looking at, that's the worksheet. You have your name on it. Yeah. That's the, well, that's the same one as that one.
It's the second.
So there's two sides.
Two of the same one.
Like I said, I didn't see you looking, but then I said, oh wait, that's the same one.
I had one finished.
Yeah. Okay, so first step, write a balanced equation. Second step, just the facts. What am I given? What am I looking for? In this one, I'm given 600 milliliters of hydrogen gas. So I have this 600 milliliters, but I see it's at STP. So as soon as I see a volume at STP, what number comes to mind? 22.4. 22.4. So, but I have 600 milliliters at STP. That's what I'm given. And the question is asking how many grams of iron 3 sulfate. So I'm looking for grams of this. So again, if we take out our stoichiometry roadmap, I'm given a volume of a gas at STP. The first step is always to convert to moles. Well, when you have volume of a gas at STP, we're going to use 22.4 as my conversion factor. Then I'm going to go to moles of unknown, in this case, moles of Fe2SO43. Then I need to go to grams. Well, how do I go moles to grams? What do I use as my conversion factor? Moles to grams. Molar mass, always. So, but 22.4, what are the units on 22.4?
Liters per.
Liters per mole, right? So what do I have to do to that 600 milliliters?
Change it to liters.
Change it to liters. Somebody else, tell me, how do I change 600 milliliters to liters? 0.6, just move it 3 places left. That's the wonderful thing about the metric system, just move the decimal. Okay? So it's going to be 0, you don't have to show word for that. 0.6 liters of hydrogen. Now it's just important that you do convert those to liters. We with me so far? Again, this is a review. We already did this one. Times, what goes here? 1 mole over 22.4 liters. That's an L. So now I have moles of hydrogen, but I need moles of Fe2SO43. So what do? Not the molar mass yet. Mole ratio, then the molar mass. Okay, what's the mole ratio going to be? 1 to 3. Okay, now moles of H2 have canceled, so now I'm left with moles of Fe2SO43, but I want grams. So how do I get to grams? Molar mass. And if you recall, we found that to be 400 grams per mole. That, it would be, how many oxygens do I have here? 12. 3 sulfurs, 2 irons. You have to add all that up. That's 400. Was this just right? Was this right as the bell was ringing? Were we finishing this one up? It seems like I recall that that's right where we were. Okay. 3.57. Okay, so it's the same stoichiometry process, taking the given to moles. We just have a different conversion factor to go to moles. And it's easier because this one, we have to add up all this. We have to figure it all out, and there's a good chance we mess that up. But with liters to moles, it's always this number. Doesn't matter what the gas is. So it's actually maybe a little bit simpler than the stoichiometry problems we did before. Okay? The key is you know to use this when you have a volume and it says STP. So, I'm going to do one more with you, then I'm going to let you do a couple on your own. So let's look at number 2. Now, number 2, it says that 14.7 grams of sulfuric acid were used in the above reaction. So we're still going to use this reaction. Okay? So we're still going to use this reaction. So now what am I given? Of sulfuric acid. So I have 14.7 grams of this. And what's the question asking for?
Liters of hydrogen.
Liters of hydrogen. So now I'm going to be X liters, but it still says add STP. So what do I start with? 14.7. So what's my next step?
Molar mass.
Molar mass, because what's the, you always take the given to
Molar mass.
moles, using the molar mass. Always take the given to moles. So, 1 mole, 98.09 grams. I think we figured that out earlier, maybe not. That's the molar mass of H2SO4. I'm assuming all of y'all know how to do that. So what, if I stopped right there, what did I find?
Moles of H2SO4.
Moles of H2SO4. But I need hydrogen. So what's my next step?
Mole ratio.
Which is going to be what to what?
3
over
3.
3. But now I need liters. So how do I go from moles to liters?
22.4.
22.4. So I'm going to say 22.4 liters over 1 mole. Now notice in this one, here we divided, here we're multiplying, because here we're going from liters to moles, here we're going from moles to liters, so we're doing the opposite. So when you do all that out, now I have liters of hydrogen, which is what I want, so I'm finished. So what do I get? 3.36? Okay, pretty straightforward. Mass to moles to liters. Or liters to moles to mass. The only difference is you're going to use 22.4 instead of the molar mass. So go ahead and try number 3. Only in the science department do you get an email, hey, I'm missing skulls and pelvis.
Oh my God.
Hey, I'm missing 4 skulls and 1 pelvis.
I wasn't sure you were looking for. I'll try to figure out. Hydrogen said H is. Is it 3? What? It's hydrogen sulfide. It's 3, right? Hydrogen sulfide is H2SO3, right?
That's minus 2.
Rip it off.
I didn't know you said 3.
No, I said that's a substrate, right?
Yeah.
Yeah. It's I took something right.
I think so. That's
Yeah,
what
I
it is.
sent it, yeah, that's what I said.
That's it. Minutes. It had to be H2.
I was in the worst actually.
Oh, H2SO3. Y'all, sulfur dioxide is going to be what?
SO2.
SO2. Obviously, we know water. I pray you know water by this point.
Wasn't that H1?
So then it says hydrogen sulfite. Well, you just come up here and look. What's sulfite?
SO3.
SO3 with a -2 charge. Everything's neutral, so how many hydrogens are you going to have to add to it?
2.
2. So the formula is going to be
H2SO3.
H2SO3. Now, the reality is that we should probably call that sulfurous acid, not hydrogen sulfite. Okay? It's really sulfurous acid. So there's your equation. What are we given?
95.0 grams.
95 grams of water, and what are you looking for?
Liters.
How many liters of sulfur dioxide
At STP.
at STP? Okay, so there's your start, so go ahead from there. More than likely on the test, I'm gonna give you the equation. So don't thank me. My wife and I have been watching a lot of Bridgerton.
Oh, God.
She likes watching Rain.
I love that show.
So, but all of that, you know, they keep referring to the guys as my lord, my lord. So I'm trying to see if I can get her to call me my lord. Doesn't work so well.
Have you watched Downton Abbey?
I don't like that.
Oh, what?
Why?
It's my favorite show.
It's actually right there on the side. You see him right there?
Yeah.
Dang it, I forgot it.
No, you should be crazy. My mom texted me and said I can't come in today. She's like, sorry about that. And it was crazy. Say what? 118. But that's not correct.
But it can be, you can make it into
Not correct.
You could. Says. I found one. I already know what it is. Let's do this.
I meant. We have a baby. My husband and Kevin, sorry. That's like one of those names people think. Those like Henry or like John.
James.
Right. Like those are the kind of names people think.
James Richard was the third.
You don't see a Steven is later.
Wait, we have a map.
Right.
The fourth. WP4. That's on the side of the last one. Yeah.
Hey, stoichiometric factors means mole ratio. So go ahead and write that on your.
Okay.
That's just your mole ratio. And it's always unknown over known.
No, that's not. Just ask her a question. You already read it.
Okay. How did you write that? That is. So we did like Stoichiometry Roadmap. Do you know how to do that?
I'm not the same. I see you.
Use this
I see you.
because you're so
It's all right.
oh shoot.
I can't pause it.
But how? Right. I'm not gonna worry. I don't have to say that. Really? You know, I'm sorry. Yeah, I just take all my stuff and I put it in like the plastic thing, and then it almost like. So now I have one too. Why is there stuff right? It's my fridge folder. I just. I think. Okay, well I'll lose that.
Alrighty. Okay, let's look at it. Alright? Now, if you're looking at your stoichiometry roadmap, you're given grams, mass. Okay? So you're given 95 grams of water. So the first step is to always take the given to moles. So to go from grams to moles, we know we use the molar mass. Then we use the mole ratio. What's the ratio? Everything's 1 to 1 to 1 here, right? So it's just 1 to 1. That gets you moles of the SO2. And then it wants liters at STP. So what do I use to go to STP?
22.4.
22.4. Okay? So we're just plug in. Now we know what we need to do. So it's going to be 95 grams H2O times 1 mole, and this is just a good one to memorize, 18.02 grams per mole. 1 mole SO2 for every 1 mole of water. And then what do we go here? Where is it, on top or bottom?
On top.
Because we need moles to cancel. You always want the unit you're looking for to be on top at the end. And all of that turns out to equal
118.
118 liters of SO2 at STP. Are we getting more comfortable with that?
Yeah.
Anything that's fuzzy? Anything fuzzy? Does your roadmap help you as far as getting a visual? Now, you don't get to have that on the test. Okay? Okay, it just kind of. Okay? So you have 4 and 5 as practice. We're not going to go over those right now, but you have 4 and 5 as additional practice problems. And if you want, tomorrow I can at least give you the answers to what those are to make sure that you're doing them right. Okay, we'll have more practice tomorrow even, but these will be 2 more practice problems of they're exactly like this. Okay? Now, let's look at our last type of problem. And it seems like I should know by now, but it's 5 tills when the bell rings, right?
Yeah, yes.
Okay. All right. So let's turn the sheet over.
Yes.
And we go to the bottom, to number 1 on the bottom. Now, this is our 3rd type of gas law stoichiometry problem. This one is going to be a bonus on the test. Okay? Not this particular problem, but a problem like this. Okay? There's several things in here one of which is going to include Dalton's law. That is not going to be bonus, but I'm going to introduce it in this problem here. It says when 950 milliliters of hydrogen gas was collected over water at a temperature of 25 degrees Celsius and at a barometric pressure of 765. Oh, it helps if we read right above it. You got to know this part. Okay? You got to know the reaction. It's a stoichiometry problem. You always have to have a reaction. Now, notice solid iron, sulfuric acid. That's the exact same equation we just used. Okay? They think it's very creative in their equations. So this equation is going to be Fe solid plus H2SO4 goes to Fe2SO43 plus H2 gas. Okay, so that's the exact same equation we had on the other side. Okay, so the first step, write a balanced equation. Again, on the test, I'll probably be giving you that balanced equation because I'll wait until the exam to be testing you on that. All right, now what am I given? I'm given 950 milliliters of this, but is it at STP? The temperature is 25 degrees Celsius, and it says the barometric pressure is 765. Okay? So I'm not at STP. So the temperature is equal to 25 degrees Celsius, and what unit do we know that always has to be in? So that's going to be 298.
Yeah.
But now it says the pressure of the atmosphere is equal to 765 millimeters of mercury. Now, why do we want the pressure of the atmosphere? I think I gave all of my big beakers back. What are the odds? Get my hand in this. Okay, so here's a gas collecting tube. Okay, I put my thumb over it, turn it upside down in here, I got a bubble. Okay, so that's an air bubble. But if I collect a gas by water displacement, I'm going to collect some CO2 gas. So I'm going to go what's happening to the water that's inside the tube? It's going down. This is a gas collecting tube. Now it measures like it's right at 7. Hey, you're gonna be old one day. I just saw on TV though that they advertised the drop that you can put in your eyes that's supposed to help. That's supposed to help for age-related readers, you know.
Prescription eye drops.
Are they prescription?
No, but like that's kind of what it's like.
Yeah, I mean it's supposed. Is there an eye drop that can change a prescription or what?
Yeah.
Wow.
How did the eye drop?
I don't know how it works, but I'm very interested in that because I hate these. Okay, because I can see great out here. I just can't see here. And so, now listen. So I'm collecting. So this is a gas collecting tube. I'm collecting the gas by water displacement. As I collect the gas, it pushes the water out. I displace the water, and now I can measure how much gas is in there. If I just did air, you can't tell what gas is air and what gas is the gas you're trying to collect. So we collect it by water displacement. So now theoretically, I was exhaling CO2. Let's just say I was exhaling pure CO2. Would there still just be pure CO2 up here?
No.
What else could be up there?
Hydrogen.
Is the water decomposing? But what might the water be doing?
Disassociate.
No. The water's going to evaporate. Remember we talked about water vapor, just the vapor pressure of water in here is that water evaporates. But notice that the level of the water hasn't gone down any in the past month, because as the water evaporates, it then goes down. There's a certain water vapor pressure that forms above this. So some of the gas that I collected by water displacement is not just the gas, the carbon dioxide, or in this case, the hydrogen. Some of it is going to be water. And Dalton's law of partial pressure says that when we have a gas, a mixture, I don't trust that, that wants to fall over. Maybe not. It'll be fun if it does. Dalton's law of partial pressure just simply says that the pressure of a mixture of gases is the sum of the total partial pressure. Let's say it this way. In this room right now, what are we breathing? Oxygen is the life-giving thing we're breathing. What's the most abundant thing we're breathing? Nitrogen. Anybody remember the percentages? 78% nitrogen, 21% oxygen. What's number 3?
1%.
Yeah, okay, it is 1%, good math. But what it makes up most of that 1%?
Carbon. Oh.
Nope, it's a gas, I'll give you a hint, it's a noble gas.
Oh, it's crazy.
Helium.
No. Helium's too light, it escapes the atmosphere. Gravity can't even hold helium.
Argon.
Argon. Okay? Okay. Now listen. Listen. 0.93% of that 1%, 93% of the 1% that's left is argon. So that only leaves 0.07%, and of that, around 0.04% CO2. And then the other 3%, 0.03%, is everything else.
I thought argon was a plant.
That's oregano.
It's on the periodic table.
I don't even know how to respond to that one. But okay, but let's refocus. So listen, 78% of all the molecules in this air are nitrogen. 21% are oxygen. Okay? So what does that mean about collisions with my body? What's colliding with my body the most? Nitrogen. So 78% of my 1 atmosphere of pressure. Take the earbud out. It's just, you're lucky it's more hassle than it's worth. Now, okay, remember what I was saying. 78% of the 1 atmosphere, so 78% of all the collisions are due to nitrogen. Which means that 78% of the pressure that I'm feeling is due to nitrogen. The partial pressure of nitrogen is 0.78 atmospheres. The partial pressure of the oxygen is 0.21 atmospheres. The partial pressure of the argon, assuming it's everything else, is just 1 atmosphere. 0.1 atmosphere. So it's just a very small fraction based upon the number of molecules. So up here, now my total pressure is going to be the pressure of the carbon dioxide gas plus some of the hydrogen gas. Now, whenever you collect by water displacement, you got to make the level in the tube and outside the tube the same. There's no way for me to know really what the pressure is of this gas in there. I don't have a pressure gauge. There's nothing measuring that. But if I make the levels the same inside and outside, let's see if I can get it close. Okay. So I'm letting more and more gas in, so the pressure, there's more and more gas molecules colliding. Okay, so now the levels are equal. Inside and outside are equal. What does that mean about the pressure inside and the pressure outside? They're the same. So the pressure of the atmosphere pushing down here is the same as the pressure of the gas pushing down there. So when I see the pressure of the atmosphere being 765, that's my total pressure. We always assume it's the same levels. That's the total pressure inside my tube, collected by water displacement. But I need just the pressure of the hydrogen. So the pressure total, my pressure T is equal to 765 millimeters of mercury, but it's going to equal the pressure of the hydrogen plus the pressure of the water. So in order to find this, what do I have to know in order to find this one?
The pressure.
Pressure of the water. Now it's real nice. Get the gray AP chemistry book. Turn to page 1099. 1099. That one actually, you can probably just pull it out.
There are over 1,000 pages.
See that page that's loose? That's it right there. You're going to look at Appendix B. Appendix B, 1099. Yeah, that'll work. Okay? Now look at the table at the bottom. It's a table of water vapor pressures at different temperatures. Okay? So this temperature is 25 degrees. So what's the vapor pressure of the water?
23.7.
23.76. So if I know that this is 23.76, in order to get the pressure of the hydrogen, what's all I got to do? Subtract it. So 765 minus 23.76 is equal to the pressure of a hydrogen, the dry gas, which turns out to be 741.24. Did I do the math right? I think I did. Okay, so this is the pressure that I use. Now, you need to know Dalton's law. Dalton, this is not bonus material. Now the key is that this number is always going to be given to you. You're going to know to subtract this out when it says it's collected over water. That means I have to subtract out water vapor pressure from the total pressure, because it's a mixture of my gas and water up in here. Okay? So we need to subtract that out. Now, okay, so that's step one. So we need to know that. So we'll do some practice of these tomorrow as well. We're probably not going to have time today.
So will we have?
Yes, you're always going to have that. This number is always going to be given to you one way or the other.
What about the pressure?
The total pressure? Yeah, that has to be given. You have to know these two in order to find that. Okay? Now, don't put up yet. Okay? Now, look at your stoichiometry roadmap. We're given a gas not at SPP. We're down here. So we have to do this in two steps. So how do I find moles? Well, I have to use PV equals nRT. Okay, now I like to rearrange. What's N going to equal? I divide both sides by RT. N is going to equal PV over RT. So now I can just plug in my pressure, 741.24. The volume, how many liters is that? 950 milliliters, how many liters? 0.95. Because this is millimeters of mercury, what value of R do I want to use? Which one do I use? 62.36. And then the temperature is 298 K. Somebody plug that into a calculator. So we're going to go 741.24 times 0.95 divided by 0.0, pardon me, 62.36 divided by 298. Okay, now listen. All of that. Y'all are killing me here. All of that is to find moles. That is not my answer. That just took me to moles. Now I have to use moles to mass to get how many grams of sulfuric acid. We won't finish that one up tomorrow since you guys have all decided that today is over. So